Hey guys, Miss Marusik here, and in this video we're going to be talking about chemical reactions. We're going to look at our different types of chemical reactions, as well as how to draw a particle diagram for a reaction. So to start us off here, just as a reminder, a chemical reaction equation is an equality between our reactants, which are sometimes called reagents, and our products. Now, I know most of you are familiar with that basic format of reactants being on the left side and the products being on the right, and of course we have a yields arrow between them. We wrote a lot of chemical reactions back in pre-P chemistry, so I know that's something that a lot of us are familiar with. But just as a reminder, the whole goal of balancing our chemical equation once we're done writing our substances would be to maintain the law of conservation of mass. We want to make sure that all of the count of atoms on the reactant side are equal to the count of atoms that are on the product side. Now, there are 5 different types of chemical reactions, and I bet once we start talking about these, you'll kind of recognize some of the names that we're dealing with. The first of those types is what is called a synthesis. This is where I have two either elements joined together to form a compound, or theoretically, I could also have 2 simple compounds joined to make a more complex compound. Now, I give each of these types of reactions kind of a nickname. So my nickname for this is married. We have our 2 singles here getting married and becoming a couple, becoming that bigger compound. For decomposition, this is where we have a compound that splits up into 2 or more pieces. So either it could split up into individual elements, or it could split up into smaller compounds. And usually we have to force these types of reactions to happen by adding energy, either running some sort of heat or electricity through the substance in order to give it the activation energy needed to conduct the decomposition. Most chemical compounds would rather stay together than split apart. So we do have to typically force these processes to happen. All right, by the way, my nickname for this one is divorce because we would have our couple splitting apart into pieces. Now, single replacement is where one element replaces another element in a compound. And depending on what kind of element we have would depend on what part of the compound it's replacing. For example, on this reaction here, what's happening is that X, when it becomes part of a compound, likes to make an anion, likes to become a negative charge. And so what will happen is it will replace the second piece of that compound, the anion, and kick that anion out to be an element by itself. Now, let's say that thing by itself was originally, say, a cation when it becomes part of a compound. So maybe it was some sort of metal. And so now what would happen is it would want to replace the first thing in the compound and kick that substance out to be by itself. I joke about these being dump your boyfriend, get a new one, or dump your girlfriend, get a new one, because you're kind of trading out. And so sometimes I'll call this also a love triangle. Now, the key thing to remember is that whenever you create that new compound, you always have to have a cation with an anion. I've got to balance those charges appropriately. Now, I will warn you, not all single replacements occur. It depends on what kind of element is this here and what kind of element would it be replacing in the compound. So we sometimes have to utilize what's called an activity series to figure out if these reactions happen or not. So for example, let's say I had a metal by itself that was aluminum. Okay, I like to think of this activity series as kind of being a ranking of who I would rather be in a compound with. So if aluminum is currently by itself, it would be willing to replace in the compound anything down here. So if any of these substances below aluminum were in the compound, then aluminum will replace it and the reaction will occur. However, if aluminum is by itself and one of these elements up above is in the compound, we would rather keep that higher up element in the compound. And so what that means is that aluminum would not be able to replace the metal, and so therefore the reaction would not take place. We also have kind of the same situation over here for the nonmetals. So this is the activity series of the nonmetals. If you notice, it kind of works in the order of what they're listed in those halogen groups on the periodic table. Now you notice on the metal side of this, a few of these have some stars, and then you see down here hydrogen, and you're like, what in the world does that mean? So when I have a single replacement that involves a hydrogen, what will happen is that any of these metals up here would replace hydrogen in a compound. It would be one of these would be enough to kick hydrogen out of a compound. However, if the hydrogen was specifically in water, then only these starred elements would be able to replace it. Okay, so these are kind of our special bunch up here that only those metals would be able to replace the hydrogen in water. By the way, you have to be really careful with water. I know we normally think about it as being covalent, which it is. However, in a reaction, it can behave as hydrogen ion and hydroxide ions when you're talking about replacements. So in both a single replacement as well as in a double replacement reaction. So you kind of have to watch out for it. Sometimes it's helpful to write it as HOH instead of as H2O to remind yourself that it does behave in that manner. All right, next we have double replacements. This is where our cations and anions would in two compounds basically switch around. So what would happen is that the cation and the anion from one substance would end up switching with the cation and anion from a different substance. So we end up creating two new compounds here. You notice I call this one wife swap. It's basically a crazy TV show where what happens is that you have these wives that switch their lives up for like a week and then they eventually switch back just to experience what the other one does. But basically that's what happens here is you're going to be switching the partners around. However, just like with single replacements, we have to make sure that we have a cation with an anion when we do that rearrangement. If we don't, then technically that is not a correct process. Also, all double replacement reactions will either be a precipitation reaction, meaning one of these compounds that we're making will be a solid, or we'll have a neutralization reaction where neutral water is formed if we put an acid and a base together. So basically, for these double replacements to occur, we either need to be making a solid or we need to be making water. One of the two will drive the reaction to completion. Without having that new substance being made, what will happen is that we would not have a reaction that occurs. So if we started off with two reactants that were both aqueous solutions, and we ended up with two products that were also both aqueous solutions, the reaction would actually not occur. And we'll talk more about that next time when we write something called net ionic equations, which you might remember a little bit about from pre-AP chemistry. It does say, again, be careful with water. As we mentioned earlier, it does behave as HOH in replacement reactions, especially when you're doing one of those acid-base neutralization reactions. That's the big time that we see water being formed there. All right, last but not least down here, we also have what are called combustions. Combustions is when I have a burning process, meaning I'm reacting with oxygen gas, some sort of hydrocarbon. Now, typically we just have carbons and hydrogens, but you could also have what is called an oxyhydrocarbon, which is carbons, hydrogens, and oxygens. So keep that in mind that sometimes these do also involve some oxygen. So you notice here, I kind of put that in parentheses. So sometimes we have that, sometimes we don't. But we're always going to be reacting it with oxygen in order to produce carbon dioxide and water. Now, a couple things here. Sometimes these problems don't mention that oxygen is one of our reactants. It just simply says, hey, I'm combusting or I'm burning this substance. And so we have to make sure that we understand that if we're doing that combustion process, that we are often going to have to add in that oxygen. Also, one other thing, you notice that the state on the water here is a gas, which is kind of unexpected. Usually we tend to see water as being a liquid. The reason here that it's a gas is because a lot of times these combustion reactions relate release so much heat as part of their process that the water will come off as a vapor. All right, let's go ahead and look at the next page. That first has some reminders about writing reactions. First off, if you ever see an element by itself, like maybe a reaction says, hey, I have oxygen gas or hydrogen gas or maybe liquid bromine, that you always want to make sure you're double checking to see if those elements are diatomic. If they are diatomic, then we have to put them in pairs of 2. Now, just as a reminder, I know a lot of you remember your diatomics from pre-AP chemistry. The way I've always remembered them is I bring clay for our new house. So it's iodine, bromine, chlorine, fluorine, oxygen, nitrogen, and hydrogen. I've heard another saying called Brinkelhoff, the BRINCL, so that's the Brinkel, and then the Hoff is HOF. So that might be another way of remembering it. Again, there's different ways to remember those diatomics, so whatever works for you. The key thing about those diatomics is that you have to put them in pairs of 2 if they are by themselves. If they're in a compound, then you don't have to worry about that. Sometimes we are asked to include states, or you're either shown states and you want to understand what those mean. So these are our symbols that we would see for those. Of course, S is for solids, G is for gas, L is for pure liquids, and then AQ is for solutions and acids. So we have to be really careful about the difference between L and AQ. L would be a very pure liquid, such as just water by itself, or maybe I melted something and so it's a pure liquid. AQ would be if you've dissolved it in water and so you have that solution present. Very rarely are we asked to predict states, but if we did have to, it's really not too difficult. Your covalent compounds, you'll usually have to have the state given to you on those. It's very difficult to necessarily predict those states on the covalent just because we see such a wide variety of states with those. However, water is assumed to be liquid unless it's involved with a reaction that has a lot of heat. For example, those combustions we talked about earlier. Ionic compounds that are not found anywhere around water do tend to be a solid. Remember, ionics have really high melting and boiling points, so it would make sense that they would be a solid at room conditions. However, if the ionic compound is anywhere near water, either because water got produced, water was the other reactant, or maybe you just had some solutions that were present, then you would want to double check your solubility rules to see whether or not it is for sure dissolved in that new solution you're creating. As far as single elements, metals we can assume are solids unless you just happen to see mercury by itself. Remember, our non-metals, we have a lot of them that tend to be gases. So, for example, hydrogen, nitrogen, oxygen, fluorine, chlorine, and group 18 all tend to be gases. Bromine is a liquid, whereas all others do tend to be solids. So, like if you saw carbon by itself, that would tend to be a solid. Or maybe you saw sulfur by itself, that would tend to be a solid. But then if you saw fluorine, F2, a sample of fluorine, we would predict that to be a gas. All right, so one of the big things that we did not do as much of in pre-AP, because we did a lot of reaction writing in pre-AP, but one thing we didn't do a lot of was writing particle diagrams for these processes. Just kind of some quick guidelines before we jump into one. If you were trying to construct a particle diagram for some sort of reaction, the very first thing I would do is write your balanced reaction first. And the reason for that is so that way you can get the right proportions of not only elements in your compounds, but also elements and compounds, the substances in the reaction overall. It's just always a safe bet to write that balanced equation first. So then, if you're not given a key for how to draw your atoms or ions, I would create one. And you can see a sample of that I've done down here. We're going to address this here in a minute. I made myself a key for my carbon, hydrogen, and oxygen on how I wanted those to look. Again, you could use different symbols, you could use different colors, you could do some things shaded in, some things with just an outline. Whatever you needed to do to designate those substances as being different would work. Okay, as long as you made your key. If you're not specified on how many particles to show, I would just simply use the coefficients of your balanced equation. And don't try and make it more complicated than it has to be. However, on occasion, you are requested to draw a very specific number of particles. And so if you're asked to do that, you would want to make sure that you're maintaining those mole ratios that you had in your balanced reaction. You want to use those coefficients to make sure that you're putting the correct ratio ratio of things together. And the reason for that is that all of your reactants may not necessarily turn into products. There's a strong possibility that one of your reactants could be in excess, and so that would mean that you would still have some of that substance remaining in your container at the end. So we have to be very careful with making sure we're paying attention to the numbers of things that we're drawing. All right, so with that said, it gives us a problem here to answer the following questions about the combustion of methane CH4. And the first thing it asks us to do is to go ahead and write a balanced equation using states. So I'm going to start off here by putting my CH4. And I'm going to leave me some space to come back and put states here in just a little bit. So I'm like, okay, well, I'm doing a combustion. So I know that my other reactant must be O2. Then I'm going to put my arrow. And this is where you would want to remind yourself that for a combustion, you would always have CO2 and H2O as your products. All right, next thing I'm going to do is I'm going to go ahead and now balance with coefficients. So even after you've written those equations for the substances themselves, things may not be balanced from side to side. So this is where I would go change my coefficients in front. I usually on a combustion start off with carbons, then hydrogens, then oxygens. That's a pretty good order to go in. So I double check the carbons and I'm like, one carbon, that looks good. So next I'm going to check hydrogens. Here I have 4 hydrogens. On the product side I only have 2, so I'm going to put a 2 in front of this water. And then finally I'm going to check oxygens. Right now on the reactant side I have 2. On this product side I have 2 and 2, so that's a grand total of 4 over here. And so in order to balance this, I'm going to put a 2 here because 2, when I double it, would be 4. All right, last I'm going to put some states. Now, this one was kind of mean. It didn't tell us that methane was a gas. However, I will remind you that methane is what comes out of our Bunsen burners when we turn that valve on the gas valve in our classroom. And so hopefully we would know that methane is a gas. Oxygen would also be a gas at room conditions. And as a reminder, for combustions, both CO2 and H2O are both gases. All right, so next it asks us to construct a particle diagram to represent the balanced reaction for that combustion. And since it didn't specify here how many of things to draw, I'm going to actually draw them in the same ratios, the same counts of things that I see up here. So first I'm going to draw my CH4, and according to this, I'm only going to draw one of it. So there's my carbon with my 1, 2, 3, 4 hydrogens. And then it says we're going to draw 2 O2s. So I said that oxygen atoms I'm going to represent with this square. So I need to not only make those diatomic, but I need to draw 2 molecules of that diatomic. So I'm going to draw 2 boxes together. And then another 2 boxes together to represent my diatomic oxygen molecules. So then on my product side, I'm going to have CO2, and I'm going to just draw one of it. Remember, if we don't end up putting a coefficient somewhere, that is an understood 1. So I'm going to draw my carbon with 2 oxygens around it. And that is linear, so I went ahead and drew it linear. Okay, now my H2O, I remember that has that bent shape, so I am going to draw that when I construct this. So for H2O, I'm going to have 2 of those molecules, each with 1 oxygen. So I'm going to draw both of those single oxygens now. And I'm going to add on 2 hydrogens that are bonded. And like I said, I'm going to do that bent shape. So that way it kind of looks bent there. And here we'll make this one look bent as well to kind of maintain a little bit of what we know about the molecular structure of those. Okay. So you can see here I have the 4 green circles here. I have the 4 green circles here. I have the 4 blue boxes, 4 blue boxes and 1 pink circle and 1 pink circle. I've maintained my law of conservation of mass from side to side. All right, let's go ahead and look at the one on the next page. Here it says, construct a particle diagram for the combustion of methane, starting specifically with 2 molecules of methane and 6 molecules of oxygen gas. So they've given us some very specific ratios to use here. And so what I did is I went ahead and started my drawing by drawing exactly what they requested me to do. My 2 molecules of methane and my 1, 2, 3, 4, 5, 6 molecules of oxygen gas. Now here, when they told me some certain numbers, what that means is that I might not necessarily be using all of this stuff to make my products. I may have a reactant that's in excess. So here's what we want to remember. For every 1 methane, I should be utilizing 2 oxygen molecules. So that means for this methane, I should be using 2 molecules of oxygen. For this methane, I should be using 2 molecules of oxygen. Well, that would still leave me with 2 molecules of oxygen left over. So we're going to need to make sure we address that at the end. First off, let's go ahead and think about one of these methanes. As we said earlier, that one methane would end up making at least 1 CO2. And I'm going to go ahead and draw it with its boxes. And as we said earlier, kind of going back to our previous picture, for that 1 CO2, I would end up drawing 2 water molecules. So I'm going to go ahead and draw those 2 water molecules here as well. And you can organize these however you want. It's really not a big deal how you draw them in here, as long as you're getting your counts right. Okay, so there was 1 of these and 2 of these becoming our product. I'm going to do the same thing for another 1 of those methanes with 2 of the oxygens. So I'm going to draw yet another CO2. And I'm going to draw, again, 2 waters. And so right now I can see my 2 pinks, so those are good to go. My 1, 2, 3, 4, 5, 6, 7, 8 greens. 1, 2, 3, 4, 5, 6, 7, 8 greens. Okay, let's check blue boxes. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Well, look how many I've drawn so far. 1, 2, 3, 4, 5, 6, 7, 8. That means I've got 4 more blue boxes to draw. But again, there's no more methane to react it with. So those diatomic oxygens will still be together in here. They were not able to react. So here's what that means. That means that this blue oxygen I'm drawing here, these diatomic oxygens, that was our excess reactant. There's some of it left over at the end. Okay. What that also means is that this initial methane here was what we call the limiting reactant. It limited how much of those products I could make, and I used all of it up at the end. There's none of it left at the end of the reaction. So hopefully those terms sound familiar. I know we talked about excess and limiting reactants back in pre-AP, but just as a reminder, this is how it would look in a particle diagram. All right, so here's what I want you to do. There's another problem on here. I want you to take just a moment and see if you can solve this. So go ahead and pause the video and see if you can try them out. All right, did you pause it? Did you go try it out? All right, let's go ahead and check and see if y'all put something similar to me. So first off, it says when calcium metal is placed into a solution of hydrochloric acid, vigorous bubbling begins to take place and the reaction vessel gets warm to the touch. And what it asks us to do is to write a balanced equation for the reaction, including states. So I started off here by writing my calcium metal and my hydrochloric acid. Okay, and I put that metal would be a solid and a hydrochloric acid I know would be AQ. So then here, they didn't actually give me my products. I had to predict what those were. So I first thought about, well, what charge would calcium become when it gets into a compound? I can see this is an element and a compound here, and so I know that this is going to do that single replacement. That calcium is going to replace somebody in here. Well, calcium ends up taking on a +2 charge when it joins up with something else. And so if I think about the positive component in this hydrochloric acid, that would be that hydrogen. So what that means is that calcium and chloride would pair up, and because chlorine has a -1 charge, it would take 2 of those to balance out calcium's +2 charge. And then what would happen is that the hydrogen would get kicked out by itself. However, we have to be really careful to remember that hydrogen is a diatomic. And so hydrogen being a diatomic, I did need to put a 2 with it. So then the next thing I did is I went and balanced this with coefficients. I said, hey, I got 2 hydrogens here and 2 chlorines here. I better be putting a 2 in front of that HCl. By the way, if you're wondering, how did I know for sure that this reaction was going to happen? Well, it kind of gave me that key in the problem itself, but also I could have double-checked this on my activity series. If you notice on my activity series, calcium is way up here above the hydrogen. So what that means is if calcium was originally by itself and the compound was with hydrogen, I would want to replace that hydrogen with calcium. I always want the higher thing up on the chart to be in the compound, which is exactly what I ended up doing here. Now, the next thing I did is I did go and put my states. As I already mentioned, I put these states here, but I'm predicting these 2 products. First off, I see I had some solutions happening on this side, which means there's a pretty good chance that this could be a solution over here. Now, I would want to double check this with my solubility rules. So if I pull those out, I can see all chloride, bromide, and iodides are soluble, and calcium's not one of these exceptions here, and so I could predict that that would be AQ. Hydrogen is a gas at room conditions. That's one of those elements that we need to know would be a gas by itself. So then the next question asks, is this a synthesis decomp, single replacement, double replacement, or combustion reaction? Well, as I mentioned just a few minutes ago, if I ever see I'm starting off with an element and a compound, my best guess is that that element would replace something in the compound in order to create that single replacement reaction. By the way, I have really good news. I know on this one we did have to predict those products. Most of the time on the AP test, they will actually give you what your products are. You might still have to write your balanced equation, but a lot of times you wouldn't have to predict those products. So you might be given this whole thing and then asked what kind of reaction it is, and so then you could very clearly identify it as being a single replacement. Okay. Next asks, what kind of evidence do you have from the reaction description that a chemical change took place? So this is what we talked about in the last video. What are those evidences that we have for a chemical change? Well, it mentioned both bubbling, so that means I had some sort of gas being made, and it mentioned that it got warm to the touch, which means heat was released. So those would be our evidences there. So then it says, hey, using the key below, draw a particulate diagram for the reaction. But it gave us some very specific amounts to start off with. It said 3 atoms of calcium, and it told us to use circles for the calcium. Now, I also went ahead and put them in different colors, but you did not have to. And then it said to use 4 molecules of hydrochloric acid. So it told me to use squares for hydrogen and these dark circles for chlorine. And so I drew 4 of those. However, if I think about my ratio up here, for every 2 of those HCl's, I'm only going to be using 1 calcium. So these 2 would use 1 of the calciums. These 2 would use another one of the calciums, but that would still leave a calcium by itself. So what happens is when I get over to these products, I do end up with an excess calcium atom still in there. Of course, when they become part of these, we end up calling them an ion at that point. And so that's why I put atoms/ions over here. By themselves, they are considered an atom. In the compound, they are considered an ion. All right, so then it says, hey, using the amounts in D, so our previous question there, which of the reactants limited how much product you could make? Well, I used up all of the hydrochloric in order to make these products over here. There's none of it remaining at the end. And so therefore that would be what we consider our limiting reactant. Last but not least, it says, hey, which of the reactants was in excess? So as we already said, I did not use up all of the calcium in order to react all the hydrochloric, and so therefore the calcium metal would be considered my excess reactant. All right, hopefully we're feeling a little bit better about reactions. We're going to be doing quite a bit of practice in class on our practice worksheet for this. So I think by the end of it, you're going to feel a lot more confident with being able to draw these diagrams, with writing balanced reactions and all of that. If you have any questions or need any help, please feel free to email me. Bye, guys.